This web talk is a think piece where I look at interesting connections between seemingly quite different modeling areas to suggest new ways of analyzing data. These connections are made possible by contrasting multi-level and single-level modeling. Some connections of this kind are well known and will not be covered here. For instance, how growth modeling can be carried out in a two-level model with data in long format, and equivalently in a single-level model with data in wide format. But there are many other connections that have not been given enough attention, I think, and that I hope you find interesting. The impetus for this talk is a new way to do latent transition analysis, but other new types of analysis are also discussed, including longitudinal factor analysis. The presentation will use some basic statistical formulas, but most of the modeling ideas will be shown in the form of figures, which are hopefully easy to understand. The figures are also useful to visually make the connections between different types of models. A key focus is how these analyses can be carried out in Mplus. And you can make connections to the Mplus website by clicking on these URLs. Mplus scripts for the Webtalk analysis are discussed in other videos. These are posted in connections with this Webtalk, together with a list of complete references for all papers that are mentioned, and the PDF handout for the talk. Slide 2 shows the outline for this web talk. A little bit over half of the web talk concerns modeling ideas, where we'll be borrowing ideas from statistics in terms of random intercepts and from psychology in terms of latent traits, and also from psychometrics, combinations of the statistics and psychology fields in terms of measurement and non-invariance. There will be some applications sprinkled into the discussions of these modeling ideas, but bullet number 2 is really where we will focus in detail on different data sets and their analyses, and we'll look at applications of latent transition analysis and extensions of that. We'll look at a couple of different data sets from the literature: mood data from Ide and Langeheine, and dating and sexual risk behavior data from Lenz and Collins, and reading proficiency from Kaplan. And then we'll ask the question at the end of that section: is LTA the right type of model? So we'll contrast it with some other modeling types. And then we'll turn, towards the end of the talk, we'll turn to multi-level time series analysis that we call DSEM, dynamic structural equation modeling, and see how the connections can be made between multi-level and single-level modeling once again. And then in the appendices, we'll take a look at sample size requirements, and that's for LTA, with the LTA extension we're going to focus on, and also for DSEM modeling. We're going to take a look at computing time, particularly with respect to the new approach to latent transition analysis, and we're going to take a look at what Mplus has done to meet that challenge of computing time. The web talk is recorded in 16 parts, corresponding closely to the tabs here in the left margin of the PDF. This makes it easier to skip parts or replay parts that are of special interest. On slide 3, we are going to turn to hidden Markov and latent transition analysis. These are two models for longitudinal data where the interest is in states changing over time, that is, categorical variables changing over time. At the top we have a hidden Markov model for 5 time points. At the bottom we have a latent transition model for 3 time points. The boxes are the observed variables, denoted by U. We're going to take them to be categorical variables, typically binary or ordinal variables, although nominal variables or count variables or continuous variables are possible as well. C, the circles in the picture, are latent categorical variables, and they are on a nominal scale. Hidden Markov models are typically measuring one variable per time point, as is shown in this picture, and usually considers very long time series, so many time points across here. And typically they actually work with only one subject or one observational unit. So for instance, could be the daily counts of epileptic episodes in a patient. In many applications, there could be up to hundreds or thousands of time points, for instance, as used with speech processing. Latent transition analysis, on the other hand, considers several measurements, several indicators of the latent class variable per time point, in this case 2. And it typically considers fairly short time series, 2 or 3 time points as in this case, or maybe a maximum of 5. Although you can certainly do analysis up to, say, 10 time points, albeit leading to very heavy computations. The typical situation is that you have a large sample of individuals, typically in the thousands. Whereas hidden Markov modeling has a long history in statistics, LTA, latent transition analysis, seems to be have a more recent history, with contributions from both sides of the Atlantic Ocean. In Europe we have contributions by Rolf Langenheine, and over here in the United States by John Graham, Linda Collins. And Linda Collins has done quite a lot of interesting work in this area, and much of it has been summarized in her book with Stephanie Lanza from 2010, Latent Class and Latent Transition Analysis. Just to get our ideas firmly planted in reality, let's take a look at an example from this article, 2008, quite influential article in developmental psychology, because it introduced a new SAS procedure for LTA called SAS-proc-LTA. And the application deals with transitions in dating and sexual risk behavior. The data are from the National Longitudinal Survey of Youth, so approximately 3,000 individuals, 3 time points, and we're looking at young adults ages 17 to 18. Items are, in this case, 3, and actually in the article they were 4 items, but 1 item is largely redundant and leads to violations of conditional independence, so it has to be deleted here in these analyses. But the analysis of these 3 items give the same results as the original article with 4 items. So we're looking at past year number of dating partners, and here's an ordinal variable with 3 categories, 0, 1, 2 or more. 3 categories also for past year number of sexual partners, and then we have a binary variable indicating whether or not you've been exposed to sexually transmitted diseases. The way you understand this analysis is by looking at measurement probabilities and transition probabilities. Measurement probabilities are given on this slide, where the columns correspond to 5 different latent classes. So 5 categories of that latent class variable C. Non-daters, daters, monogamous, multi-partner safe, multi-partner exposed. The row sections here correspond to the 3 observed items, and the interpretation of the latent classes is obtained by looking at the pattern of probabilities. So for instance, non-daters are characterized by having a high probability for having 0 dating partners and low probabilities for the other 2 alternatives. Number of sex partners, 0, and exposed to STD or not, high probability of the no category. So the high probabilities here identify this class as non-daters. In contrast, you have the daters, where you have a high probability for at least 2 dating partners, but 0 sex partners. So just daters. And exposed to STD is a no with probability 1. The monogamous class is characterized by a higher probability for 1 dating partner and 1 sex partner. Ambiguous picture for the STD. Multi-partner safe has at least 2 partners with high probability, at least 2 sexual partners with high probability, but not exposed to STD. So that's where the safe part of that name comes from. Multi-exposed has the same pattern of probabilities for the first 2 items, but has an elevated probability for being exposed to sexually transmitted diseases. On slide 7, we have the same columns, but now the rows are also the latent classes. So we have a cross classification. So on the diagonal, you see high probabilities, bolded, that corresponds to staying in the same class. So 0.627 is the probability that if in a year you were a non-dater, you will be a non-dater in the following year with this probability. Same thing for daters, for monogamous. Multi-partner safe have a little bit lower probability of staying there, and some non-ignorable probability of transitioning to the multi-partner exposed, the risky class. For multi-partner exposed, high probability of staying in that same class, but a certain probability of going back to a monogamous relationship. So that gives you an idea about the central parts of the LTA model. So as we discussed, we talked about the measurement probabilities, that is the relationship between C and the U's. We talk about the probability of U given or conditional on the C variable. It's really a latent class analysis for each time point, where we typically would have measurement invariance across time. So the probabilities would be held to be equal across time, so that we're sure that we're considering the same latent variable construct. For the latent part, or the structural part, as we say in structural equation modeling, you can break it up into initial status probabilities, probabilities for the first time point, and then transition probabilities for C2 given C1, C3 given C2. So they look like this. And that's the model that's been used quite a lot. There are extensions, for instance, to mover-stayer modeling, where stayers is that is a latent class variable really, with 2 categories. So one more latent class variable, where the stayers are individuals who will remain in the same class at the next time point with probability 1. So the diagonal elements of the transition matrix are 1s, and the off diagonal are 0. You have 0 probability of transitioning. And that typically picks up a substantial percentage of the sample, whereas the mover class, is like in regular LTA. They can move or they can stay. You often do multiple group analysis, that is, you have observed groups, divisions of the sample as opposed to the unobserved division of the mover-stayer. You usually look at measurement invariance, so measurement invariance across groups, not across time. For instance, do males and females have the same dating transitions. Covariates are often brought in, covariates that influence latent class probabilities as well as transition probabilities. And as a matter of fact, you can also let them influence the observed variables, which then gets back to the issue of whether or not you have measurement invariance. Now we can look at these models, hidden Markov and latent transition analysis, and there is something missing in these models that make them unnecessarily restrictive. There's a simple extension of these models which makes them much more flexible and presumably will fit the data better and give better estimates. We're going to take a look at what's missing in these models from several different perspectives. We're going to consider both single indicator measures per time point and multiple indicators per time point. In the single indicator case, we're going to take a look at a statistical perspective, where we're going to bring in multi-level modeling thinking, because after all, LTA has level 1 time and level 2 subject, if you want to look at it that way. Time is nested within subject. And from that statistical perspective, we're going to talk about random effects, especially random intercepts. And then we're going to take a look at the substantive perspective and look at latent trait theory in psychology. And that leads us to consider between subject differences that are stable over time. And then we switch to multiple indicators per time point and take a psychometric perspective, where we're going to look at issues of measurement non-invariance, both in the context of multi-level factor analysis and multi-level latent class analysis, and relating that multi-level latent class analysis to the latent transition analysis situation that we're interested in. On slide 10, I give you a quick reminder of logistic regression, which is a key building block in latent transition analysis and factor analysis with categorical outcomes. Probit regression is also possible, but perhaps logistic regression is more common. So what I'm doing here is trying to connect a picture of what's going on with a formula, equation 1. So in the picture, on the x-axis, you see a continuous covariate x2. You can think of that as age. And on the y-axis, you have a probability scale going from 0 to 1 for the probability of you being equals 1, say having lung cancer. And also we have a categorical, a binary x1 covariate, a dummy variable, which could be a smoker versus non-smoker. And we see that with increasing age, the probability of getting lung cancer increases. But we also see that for a given age, the probability of getting lung cancer is higher for those who are smokers than for those who are not smokers. 0.75 versus 0.25 in this case. If you look at the formula, everything happens here in the in the expression in parentheses, where you don't have any residual part, but you only have the linear function of the x's. And we see that the curves are parallel because beta 2 is the same, the slope for x2 is the same irrespective of the x1 values. Otherwise we would have an interaction term between x1 and x2. Beta 2 is positive, and we also see that beta 1 is positive because the probability is higher for smokers than for non-smokers. So we learn then that higher values of this loaded expression correspond to higher probabilities of u equals 1. If we didn't have x2 at all, even with x2, we have two intercepts essentially here then. When x1 equals 0, we have beta 0 as the intercept, and when x1 equals 1, we have beta 0 plus beta 1. So that's a positive increase of the intercept and therefore a positive increase of the probability. Now, we're going to take a look, use this kind of formula in settings where the x's are unobserved. They're latent variables. In factor analysis and item response theory, we're going to work with x2 as a factor, as a continuous latent variable. And in LTA, we're going to work with x1 as a latent class variable. So in this case, a binary latent class variable. So it's a very general formula that we use. So here's the formula again. And to understand it further, we recall that it relates to odds and odds ratios. The odds for u equals 1 is the ratio of the probability of being u equals 1 divided by the probability of u equals 0, or more generally 1 minus probability of u equals 1. Probability u equals 0 is 1 minus this expression. And if you can express this ratio with the help of equation 2 and take the log of it, you get the so-called log odds, which is referred to as the logit. So the logit of this left-hand side expression is the log odds, and that is this linear expression that is in the parentheses. So the logit is linear, and we're used to dealing with understanding linear expressions. Now you interpret the influence of x on u in terms of odds ratios. So to get an odds ratio, you take, since you have log of something here, you take the exponent, you exponentiate it, and therefore log and exponentiation cancel each other out. So you will have the exponentiation of this expression. And that implies that the influence of x1 on u, for instance, is e to the power of beta 1. So you relate being a smoker versus not a smoker to getting lung cancer versus not lung cancer. So an odds ratio is the relationship between two variables. Now, there's much more to say about this, obviously, and it's described, for instance, in our book, which you can find on our website, together with scripts for over 100 examples. And all the chapters are described here. Now for the latent class situation, latent transition analysis situation, it's even simpler. So here it's, for instance, if you talk about measurement probabilities, you will have, for instance, a binary latent class indicator u and a latent class variable c. You can think of them as binary, both of them. The probability that you have u equals 1 when the latent class variable is in class C, lowercase c, is the logistic expression, where L is the logit for class C. And so the logit of this probability expression of this is log of the odds. And in the latent transition or latent class analysis setting, there are no x2 variables, no continuous variables, but only an intercept, beta 0, which varies across the latent classes. In Mplus, you instead work with thresholds because they are more general and can handle ordinal variables, so more than 2 categories. So you can have more than one threshold. And they are the same as the intercept, but with a negative sign. So you think of this as high logit giving high probabilities, high thresholds giving low probability. Threshold is something you have to get beyond to get u equals 1. And you know then that when logit is 0 and when the threshold is 0, they're 0 at the same time, we get probability 0.5, neutral point. Low logit, high threshold gives a low probability. High logit, low threshold give a high probability. So up here we talked about how to get probability of u equals 1 as a function of the logit. And then we just remind ourselves, how do you get the logit from the probability, the reverse? Well, again, the logit is the log odds. It's the log of the probability ratio. So if you have a probability that you want, you can calculate the log of that ratio, and that is your logit. So you can go back and forth in that fashion. On slide 13, we take a first step towards trying to answer the question what's missing in regular latent transition analysis. First of all, we recognize that we're talking about longitudinal data analysis. Second, we can view the data also as nested or hierarchical data, where we have time nested within subject. In the latent transition analysis model, we have U being influenced by or predicted by the latent variable C. We're going to make it a little bit easier by, instead of C, we're going to consider a unobserved covariate X influencing the binary U variable. So let's take a look at a two-level model formulation for this, where level 1 is time and level 2 is subject. So on level 1 we have the usual logistic regression expression that we discussed in a previous segment. So we have a dependent variable, which is the logit or the log odds for the probability of U, and we write that in the form of an intercept and a slope times x part. Now the interesting thing is that the intercept is random, has a subscript j, so it varies across subjects. And on level 2 then we can write that variation across subjects in terms of a beta 0, which can be seen as the intercept mean, but we also have variation, a residual, which is then saying that certain subjects have a higher or a lower value than the mean. And the variance for that residual is a parameter sigma squared U. So Uj, that's a description of the dependent variable level, irrespective of the influence from X. Now in terms of a model figure, we can describe that in this way, in a two-level long format. You have a U regressed on an X, logistic regression with slope beta, and we have a random intercept, which we denote by a filled circle here on the time level, and it becomes an open circle, a continuous latent variable on the between subject level. So you have the parameter beta, and you have parameter the mean, beta 0, and variance sigma square U, 3 parameters up here. Certainly if you do two-level modeling, you would never dream of at least having the intercept being random. You wouldn't want to have that to be fixed and the same for all subjects. You could also have the slope being random, but typically the most important piece to make random is the intercept. Now we can write this two-level model in a single-level format in quite equivalent way as we have shown here on the right. So here you have 3 time points. U is measured at 3 time points, influenced by X at the 3 different time points, different values of X at the 3 different time points, with slope beta, which is in common for all time points. Beta does not have a subscript t here. And then U, the random intercept, influences the U variables directly with fixed coefficient 1, corresponding to the invisible 1 multiplying U sub j here, so that it's the same, it's not varying across. The influence of Uj is not different for the different time points t here. Once again, you have 3 parameters, beta, mean of this, beta 0, and variance of this. Alternatively, you can have the mean of the random intercept being 0 and put that level related parameter here instead as thresholds, for instance. Thresholds then are held equal across time. So if you analyze data here, you can arrange it in long format or wide format And if you do maximum likelihood estimation, you're going to get exactly the same log likelihood value and exactly the same parameter estimates. So it's an equivalent formulation of the same situation. Now on slide 14 we make a little bit of an aside talking about panel data, particularly in econometrics, where we have a interesting idea of being able to deal with time invariant omitted variables. If you look at this equation here, once again, u sub j intercept, and then we write out the intercept beta sub j plus epsilon j, and then we have a beta x term. Why that random intercept part, that is, why that residual is so important, is because if you have left out, not measured some variable z, a time invariant subject varying variable, whatever it might be, a continuous variable here, it can be picked up by a random effect here so that the estimation of beta doesn't get distorted. So that's the positive part. Now econometricians have criticized the random effect approach to this by saying that it's likely that this u variable, u sub j here, is correlated with x. That is, you should really include a correlation like this. This is how the model should look. Because the u sub j, as we said, it's a function, it represents rather the level of the dependent variable, higher or lower. And that dependent variable phenomenon or characteristic is likely to be correlated with the between level part of the x variables. The between level parts of the x variables are likely to be correlated with this between level part of the y variable. So these correlations. And that's true, but that's not a problem for us if we do this multi-level modeling correctly. So for instance, if you have this logistic regression equation in two parts, level 1, level 2, you can group mean center the x's by subtracting the group mean from each x observation, and on level 2 you can add the group mean variable. In fact, it's sufficient to avoid this problem, it's sufficient to include this group mean variable and keeping the x variable as it is, the whole full x variable here, because once we have included the x bar here for uj, the residual delta j will be likely to be uncorrelated with the full x, because the group mean has been included here. That's the Munlach formulation. I can give you references on that later on. So the critique is not really a problem for us, and in fact we're not going to work with time varying covariates here in the models that we're going to take a look at. But you should keep in mind that if you do, you want to take a look at this formulation, which is then described in Wright and Bush and Breich. Table 5.11, for instance, discusses exactly this beta sub w and beta sub b, the within level beta and the between level beta, and the difference between them is the contextual effect. Anyway, this is a good model to separate within level phenomena from between level phenomena. Now you can do even better than centering with x bar j, the observed sample mean. You can use latent variable centering, and my colleague Tihomir Asparhov and I have written a paper that appeared recently in the journal Structural Equation Modeling. Now when it comes to this fixed versus random effects literature, which you should be aware of so you're ready to answer any critique, you have econometric sources like Wooldridge, Econometric Analysis. He also has an econometric textbook covering this. Paul Allison has done some nice work on this in several papers, trying to convince econometric researchers that you can handle random effects modeling just fine, and it actually is better than fixed effects procedures. Boland and Brandt had a paper here describing structural equation modeling, how this can be done in a general fashion within the SEM framework. a very nice article in Political Science Research and Methods by Bell and Jones, talking about this same matter, very clearly laid out. And Bu and Satora has a nice application with business examples in organizational research methods. And John Antonakis has a nice recent overview as well of this in organizational research methods. And then Ellen Hamaker and I have a paper that's coming out in Psychological Methods, where we describe the connection to multi-level modeling to try to clarify this issue further. Now, on slide 16, going back to then the single indicator LTA, that is the hidden Markov model here, we have learned then that what it really should look like is like on the right, adding a random intercept influencing all time points, a time invariant effect, a time invariant variable. And that has not been very much used, however, in hidden Markov modeling. Probably because the hidden Markov model on the left can use the fast backward-forward or forward-backward so-called Baum-Welch algorithm for ML estimation. Because you have the simplifying feature of the U's being uncorrelated, independent, conditional on the C's. The U's are only connected via their connection to the C's. And when you look at this model on the right, you lose that simplicity. The U's are no longer independent, conditional on the C's, because they are still correlated with help of the U variable. This means that if you consider maximum likelihood estimation, it's going to need numerical integration with respect to a single dimension U, which leads to much heavier computations in this mixture setting that characterizes latent class and latent transition analysis. It's a mixture of different classes. If you want to read about estimation matters, there is a 2012 book by Bartolucci and others, Latent Markov Models for Longitudinal Data. There is, however, an application of this random intercept hidden Markov modeling on slide 17 by Altman in JASA, Journal of the American Statistical Association. And she considered relapsing remitting multiple sclerosis patients, a sample of 39 subjects, where symptoms worsen and then improve in alternating periods of relapse and remission. So the outcome here is the number of lesions in the brain. It's a count variable, which makes the computations even more difficult. The number of time points, T, is 24, monthly scans for 2 years. And you consider two latent classes, these hidden states of relapse versus remission. It's an impressive work, particularly since unlike other maximum likelihood estimation, this is not with mixture models. This is not done by the EM algorithm, but actually observed data log likelihood optimization. I think it was her dissertation, actually. So on slide 18, we are again taking a look at what's missing in latent transition analysis. And we talked about the statistical perspective. We're still within single indicator per time point in that situation. Now we're turning to the substantive perspective. And we're going to talk about trait theory and psychology and between subject differences that are stable over time. Here's an interesting model. If you just look at the picture first without concerning yourself with the interpretation of the variables, it looks like the Altman model for hidden Markov modeling with a random intercept up here. Because we have these variables S1, S2, S3, S4, for S5, which looks like the latent class variables and transitions between them over time. But in this case, we have continuous variables throughout. So y, the observed variables, are continuous, t is continuous, and the s variables are continuous. So this is a model that was brought forward by David Kenny and Zotra in 1995, the trait state error model. So t here represents a continuous latent trait variable. So something that influences the variables at all time points. So one quantity influencing the variables at all time points. So it sounds very much like a random intercept. The S1 through S5 represents a continuous latent state variable, so something that is not as stable as t, but varies across time. And we have then also measurement errors in each of the y variables here. So it's a model that is actually quite interesting because it has more circles, more latent variables than observed variables. You may also contrast it with the logistic regression model, two-level model that we looked at, where we had x's down here instead. But in that case, we did not have any relationship between the x's. Just to describe and think about the visual aspects of the modeling. Now, in terms of what the model means here, it's very important that this trait variable influences the y variables and not the s variables. So each y variable is influenced by the trait and by the state and a measurement error. So the state variable then is not a measurement error and not a trait. It's something different than those two, something uncorrelated with those two, which means that this is a trait-free and measurement error-free variable, and it's that variable that we're interested in changes over time of. And these are standard linear regression. So the s variables are therefore free of the t, of the trait influence, and free of the measurement error influence. And that's a key aspect here, the fact that t does not influence the s's, but influence the y's. And what then remains of the y's is the s, apart from the measurement error. It's a very interesting model. So slide 20 then, there's some literature, reading suggestions here. Cole had a 2005 Psych Methods article on extensions of this model for multiple indicators. And Kenny and Zotra came back in the edited book from 2001, New Methods for the Analysis of Change, where he called his models the STARTS model. An application by Wagner here in Journal Personality, Self-Esteem, Mostly Stable. So it has a big trait component in young adulthood. And then we have a Lütke article in Psych Methods, where he recognizes that this STARTS model can have computational difficulties, perhaps due to this high ratio of latent to observed variables. And he is proposing here a Bayesian approach using MCMC techniques to have a little bit better result using in the estimation of the parameters of this. Now on slide 21 we move to a situation where we talk about cross-lag panel modeling. So we have two processes going forward instead of just one as in Kenny and Zotra. X and Z influencing each other, and with a auto-regression for each variable, and then residual correlations over time. Now, there's an interesting article by Hamaker and others in Psychological Methods where we have a critique of the cross-lag panel model laid out, and that standard cross-leg panel modeling is criticized on the grounds that, here we quote from the abstract, if stability of constructs is to some extent of a trait-like time-invariant nature, the autoregressive relationship of the CLPM failed to adequately account for this. The lag parameters that are obtained with the CLPM do not represent the actual within-person relationships over time. This may lead to erroneous conclusions. An alternative model separates the within process from stable between-person differences through the inclusion of a random intercept. So this is a little bit like separation in Kenny and Zotra's model, where T does not influence S directly, so the influence between the S's over time is free of trait influence. Here's how Hammacher and others draw their model. So we still have the Y variables and we have the Z variables going forward at 3 time points. And we introduce now 2 random intercepts, one random intercept Y for the Y variables and one random intercept Z for the Z variables. So you have then a bivariate random intercept model here, and fixed coefficient 1 for the Y and for the Z influence on their variables. And then these circles then become free of random intercept influence. So because for each latent variable here, it influences the part of Y that is not the random intercept. So very much like the thinking of Kenny and Zotra in that way. So that the relationship between Y and Z over time, cross-lagged, is free of this random intercept influence. So the random intercept is then thought of in a multi-level fashion as a between-level variables. So you sort out the between-level variation of Y and the between-level variation of Z, and you can then look at the within-level relationships between Y and Z. So once again, it's a multi-level type of thinking, but presented then in a single-level wide format. So you have then Hammacher's article here and several Mplus scripts for that article on the website here. Scripts for the how to run the RI-LTA, how to run a multiple indicator version of it, and other resources. So on slide 24, we now move from the single indicator situations that we've looked at, and we'll take a closer look at multiple indicators per time point, which is really the setting that latent transition analysis is focusing on. We're going to take a look at this from a psychometric perspective, where we'll get into issues of measurement non-invariance and multi-level modeling of both factor analysis and latent class analysis. Slide 25, we have a situation where we are concerned about response bias in self-report questionnaires. So it has been mentioned in the psychometric literature, starting with 1940s psychometric monograph by Wolf, concerns about the individual differences in intercepts and loadings in factor analysis models due to response styles like acquiescence or social desirability. And this was picked up by Maydew, Olivares, and Kaufman in 2006 Psychological Methods, where they introduced the random intercept factor analysis, where individual differences are captured by an added response style factor with factor loadings fixed at 1. So it is a random intercept factor. Different individuals are allowed to have different intercept values. This has been applied, for instance, in European Journal of Psychological Assessment in this year by Schmalbach, from bidimensionality to unidimensionality in self-report questionnaires, with applications to a series of established questionnaires for depression, procrastination, etc. So the model that Maydew, Olivares, and Kaufman considered looks like this. Once again, if you just look at the picture, it looks quite familiar, with a random variable sitting up here, be it a random intercept or a latent trait, influencing different variables the same way with loadings coefficients 1. Down here you have the factor analysis model that you're interested in, with its loadings lambda 1 through lambda 5. And in formulas for a categorical outcome U, look at the logit of that as a function of the factor. We have an intercept which is varying across the variables, the factor indicators. R goes from 1 through 5 in this case. Nu is how you read that symbol, using the literal all Y type of parameterization notation. And then you have a random intercept part here, U sub I, varying across individuals I. And then you have the factor model that you're really interested in, lambda for item or indicator R, multiplying the factor value for individual I. So here we then have a random intercept with mean 0 and variance sigma squared. Alternatively, you could say that the mean is nu R and put the mean in here. But it's the same thing. UI is a random intercept factor with loadings fixed at 1 for all the factor indicators. So we actually add only a single parameter, sigma square, the variance of this, to the regular factor analysis model. And by being able to pull that U, random intercept variation, out of the U variables, F, the influence of F, pertains to what's left in the U variables. So taking into account, or taken care of, the variation across individuals that's constant over all items, and eliminating that before you do the factor analysis. So essentially then, we're capturing measurement non-invariance by this random intercept. That is, the measurement qualities, in this case the intercept, vary across individuals. So it should allow for better estimation of the model of interest, namely the factor loadings. And it suggests also that measurement non-invariance is okay if modeled. But you can ask, is the model really realistic? Different indicators may have different random intercept variance after all. But we can't identify that. What we would need to be able to identify that is a design where each indicator is measured multiple times, such as with multi-level data, students nested in schools, so you can have a factor analysis intercept that can vary across schools. Or longitudinal data where time is nested within individuals, so that an intercept for each indicator is allowed to vary across individuals. So the random intercept factor analysis model is useful because it takes a step in the direction of capturing measurement non-invariance in the sense of an intercept parameter being different for different individuals. But there are other settings where we can go a little bit further in terms of allowing for measurement non-invariance. On slide 28, we turn to another example of multiple indicators in cross-sectional data, namely multi-level factor analysis. So we're going to take as a standard example students observed within schools. So we have a between-level part of the model and a within-level part. The within-level part has to do with student variation, and the between-level part has to do with school variation across schools. So here we're looking at 3 items. In this case they're categorical, and we're assuming for simplicity a single factor on the within level, FW. And as usual, we have a factor model where the arrows have coefficients corresponding to the factor loadings lambda. And we have residuals for those indicators. But also we have this filled circle notation, which indicates that we have random intercepts. So intercepts for these 3 variables that vary across schools. So we have these latent variables on the between level corresponding to the random intercepts. So they are continuous latent random intercept variables. And they can also be, their covariance matrix can also be structured by a factor model. In this case, for simplicity, a single factor, F between, that influences each of the items with different loadings and with residuals as well. So it's like having a factor analysis model on within and another factor analysis model on between. Typically you have many more factors on within than on the between level. The within level, and that's because the within level has to do with variation across students or across individuals, which is typically larger than the variation across a cluster unit such as schools. And typically you would have many more factors on the within level than on the between level. So on the within level you could have abilities represented by representing mathematics, reading, science, performance, so maybe 3 factors, whereas on the between level those same subjects, the variation across them with respect to school variation could be represented perhaps with a single factor, school excellence or something like that. And there's therefore no need to expect, or no reason to expect, that you would have the same number of factors. And even if you have the same number of factors, there's no reason to believe that you have the same factor loadings on within and between. So here we have a situation where we allow a random intercept for each variable, for each factor indicator, in this case letting them vary across schools. So you can ask yourself, actually, then, if you think back to the previous slides talking about random intercept factor analysis, perhaps you could then also add a random intercept factor on the within level to represent variation across individuals, across students, and that's common to all of the items. I don't know how relevant that would be. I don't know if that has been done. Now the multi-level factor analysis model can be thought of as a model for the within and between level variation. So you can write the vector of responses, in this case for a continuous variable, where the multi-level factor analysis started, in terms of between and within level variation. So these are actually then random latent variables, and that can be obtained by a random effects ANOVA, or multivariate random effects ANOVA. You can actually create sample covariance matrices for these vectors, and vector meaning that we are looking at all of the items, 3 items according to the previous slide. And then you can impose a factor structure for each of these parts, the between part and the within part. So here you have the between part. It's a factor loading matrix multiplied by the factors on between plus some residual on between. And the YW part can be written in terms of a factor model with W subscripts. So you have a covariance structure for the Y, which is sigma B plus sigma W, where each covariance matrix has a factor model structure lambda, psi, lambda prime plus theta, where psi is the factor covariance matrix and theta is the residual covariance matrix. We would just add the subscripts B or W on these 3 parameter matrices. It's interesting to think a bit more about equation 8. For instance, if you move yb over to the left-hand side, the observed y minus the yb yields you yw within variation. So you have latent variables centered the y variable, which I referred to in passing in previous slides. Now, multi-level factor analysis seems to have started in the 1970s. Here's a fellow Swede, Kjell Härnqvist, who wrote an article in 1978 about primary mental abilities of collective and individual levels, so class or school level and student level. And I think he visited Stanford earlier, where Lee Cronbach had been working on a research project that related to multi-level modeling, early multi-level modeling thinking. I think Kjell Härnqvist was inspired by that. And much later, a decade later, a statistician jumped in, Harvey Goldstein, and Rod MacDonald wrote a paper in Psychometrica where they looked at these covariance structures on between and within. And then MacDonald and Goldstein came back and made a publication in the British Journal of Mathematical and Statistical Psychology. If you want an overview, you can take a look at my paper from 1994 in Sociological Methods and Research, where I give a little bit of a literature overview and show how this modeling can be easily fitted into a structural equation modeling framework. Now going to slide 30. Now if you look at one factor indicator at a time for individual I in school J in this case. So we have then the logit model written in terms of now on the variable level instead of so scalars instead of matrices. New intercept in the, again, literal y only notation, the intercept and the between level variation, and then the within level variation. And again, there's no within level residual. There's no residual in the logistic regression. Now, I condition then have a condition on dot here. It means that you condition on any random quantity on the right, by which I mean that I'm not talking about the marginal probability of u being 1, but I'm talking about the conditional probability as a function of these quantities on the right. The marginal probability would integrate out all of these, sum over all of these random variables. Now we can write this model, which at first we think of as a factor model for a between level covariance matrix and a factor model for a within level covariance matrix. We can instead express it by two equations like this, where u sub j is seen as a random intercept for this item in this school, and that random intercept has an intercept nu and then is regressed on the between level factor and its residual. So if you plug 12 into 11, then you get 10. But it's written in a very suggestive way here. That is, we think of the factor model on between as being a structure for the random intercept. So it's totally in line with two-level logistic regression with a random intercept and fixed slope. So the random intercept varies across the level 2 units, that is schools. Now if you take this a little bit further on slide 31 and think about it more, what does a random intercept mean? Well, it means that you don't have the same intercept in all of the between level units. So we can think of that as a measurement non-invariance matter. You know, we have a measurement model here, observed variables u as a function of latent variables, factors on within and between. So we don't have measurement invariance, we have non-invariance with respect to the intercept. This has been written about in the continuous outcome setting by Yak and others in the Structural Equation Modeling Journal, and by me and Tiomer Asparaho in SM&R, Sociological Methods and Research, where we compare this random effects modeling of measurement non-invariance to the alignment approach in Mplus. For categorical outcomes, it's been written by Jean-Paul Fox and in British Journal of Mathematical and Statistical Psychology, and by Fox and Glass in a 2001 psychometric article. And again, these references, the full format references, are given in a separate document that's posted together with this Webtalk. So you have measurement non-invariance, but it's okay because you model it, you take it into account. So it's a random effect version of measurement non-invariance. And the thinking behind that is a little bit further explicated in this literature. Now, just to expand the horizons a little bit here, in multi-level IRT, multi-level item response theory, for test items, this random intercept notion is also used. Again, Jean-Paul Fox, he wrote a 2010 book related to this, and he has an article in an edited book, Random Item Effects Modeling for Cross-National Survey Data. And essentially it's a variation on this multi-level factor model again. You have a logistic regression here with a random intercept, and the random intercept is given a factor structure here. Now, multi-level IRT, in my readings of it, seem to, by and large, mostly, assume that the loadings are the same on the within and between levels. So these loadings are the same, and that there are no residuals on the between level. If you make that assumption in equation 15 and 16, you get to equation 17 and 18 down here. So you have one lambda, that's the first line, and you have the same lambda on the second line with residual 0. Now, if you write it that way, then you can think of this as a random intercept for the factor. That is, you can rewrite 17 and 18 as 19 and 20 by writing lambda times Fij, where Fij is the sum of the between and the within variation. If you multiply that with lambda Fb times lambda Fw, then multiply by the same thing, then you have equation 17 and 18. So you have one random intercept for the factor, not a separate random intercept for each u. So if you think in terms of maximum likelihood estimation and numerical integration, you have smaller number of dimensions of integration, easier computations. Now, if you look at this in terms of pictures, then first we have two types of multi-level factor models. First, I talked about the multi-level factor analysis setting, and then I talked about the IRT setting on the right. So let's look at this carefully then again. On the left-hand side, within variation, this is within school variation, so variation across students. It influences the part of the observed variables that are not influenced by FB. So these filled circles mean that we have taken out the between level variation in the items, and FW influences what's left in the U variables, namely the within variation. And on between, then you have these random intercepts for each variable, which you may or may not want to structure by a factor. They could be totally unrestricted too, except that would, in maximum likelihood estimation, lead to a lot of at least 5 dimensions here. And you have a residual. This is the epsilon b residual for each item in between. If you want to, and I think I did in early drawings, you can connect these U circles to the U boxes here. So you can see that they are influencing part of U. Now, but we have a clean separation of within and between variation. Now in the IRT setting, we put the random intercept not on the items. There's not an item-specific random intercept, but a random intercept for the factor. So dot down here, and that dot is the F between factor. So according to the previous slide, formula 20, F is part F between, part F within. And then there are no residual arrows here like there are on the left-hand side. So this is a different formulation where F is no longer pure within variation, but it consists of both within and between. As a matter of fact, you may prefer to write this model in a different way by having an FB factor sitting down here and influencing the FW and thereby influencing the items indirectly, because the IRT model imposes equality of the loadings on between and on within. So that would be perfectly okay to let the between factor influence the within factor, because then it would influence the items with the same loading as the within part. So just getting used to different pictorial descriptions of the models. On slide 34, we make a comparison between the multi-level approach taken in factor analysis and the multi-level approach taken in latent class analysis. And that becomes quite important for the latent transition analysis that we will get to. So on the left, you have the same model that we talked about in earlier slides. You have a within factor model with random intercepts, and they are continuous latent variables on the between level. And if we want to, we can describe the correlation between these by a single factor. And we typically would want to have residual variances as well, although they are often quite small when you talk about clusters such as schools or communities, and they can actually then be ignored. Now, on the right-hand side, you have the tradition in latent class analysis, which seems to be in the original approach to multi-level modeling. So here you have the same 5 indicators, and now you have a latent class variable, C, influencing the indicators or making them correlated, instead of the FW continuous factor that you have here. You have then the nominal latent class variable C. And here's a case where we have 3 categories, 3 latent classes for C, which means that you have 2 intercepts, or means if you want to describe them that way. So 1 less than the number of categories, because the probabilities have to sum to 1. So you get 2 random intercepts, which then are continuous latent variables that vary across the clusters, be it schools or communities. And we can make them correlated, and if there are many classes, there will be many random intercepts, and you may want to simplify things by putting a factor between them to describe the random intercept covariation by a single dimension instead of many. On slide 35, I repeat the model that we just looked at on the left-hand side. And again, that seemed to be the original attempt at multi-level latent class analysis put forward by, for instance, Jerome Vermont in articles 2003 and 2008. And Tiamer Asparahov and I also did some work on that and wrote a chapter in a mixture book, 2008. What we focused on, however, was to try to move from left to right. That is, we want to put the random intercepts on the indicators themselves rather than on the latent class variable. So the indicators have random intercepts, and they become continuous latent variables on between. And to reduce the dimensionality, you could put a factor behind them, and reducing then the numerical integration in maximum likelihood estimation from 5 to 1. which you get if you don't have these residuals. They are typically quite small in applications when the between level corresponds to clusters, as opposed to individuals, as we will see later on. Why this formulation is important is that when you turn towards latent transition analysis, you want to look at the latent class variable at a certain time point influencing a latent class variable at a later time point. And what's nice about the formulation here on the right is that C represents within cluster variation, clearly separated out between variation already on the observed item level. So all that between level variation is pulled out of these boxes, and C influences the within part of the boxes, so to speak. So then C on C here, the influence between C's over time, becomes a within level influence. On the left hand side, however, C here now, just like in IRT, contains both within and between level variation. And if you have then a latent transition analysis built on that, you will confound within and between level variation. Now let's take an example of the model on the right from the applied paper by Henry and Mutén. So that appeared in the Journal of Structural Equation Modeling, and it had to do with adolescent smoking typologies with individual and contextual predictors. So we're looking at over 10,000 individuals in 206 communities. So these are the clusters. 6 categorical indicators and 3 classes were found describing various kinds of student smoking behavior. And random intercept variation was found for the indicators, which represents a cross-community variation and particularly strong variation for certain items, and where the variation was related to the proportion of youth living in poverty. So for instance, most friends are smokers, that item, had a much larger probability of being endorsed in communities with a large poverty proportion. So you can have these between level 2 variables influencing the random intercept. And you can think of this variation across communities as a form of measurement non-invariance. In this case, particularly so for most friends are smokers. On slide 37, we will be going deeper into multi-level factor analysis and see where it can take us into new kinds of analyses. So we have the standard multi-level setting here with a prototypical example of students observed within schools. So we have a random intercept for each of the factor indicators, the student level factor indicators. Those random intercepts then become continuous latent variables on the school level, and those continuous latent variables are indicators of a between level factor, which could be seen as school excellence or something of the kind. So this is a cross-sectional situation with students within schools or students within classrooms. So it's a hierarchical situation, students nested within schools. But the case of time points nested within individuals is also multi-level. So couldn't we apply this model also to longitudinal data? What would that look like? Well, I think then that multi-level factor modeling can actually teach us how to do longitudinal factor modeling, in this case for 2 time points. So here we have the cross-sectional model, and it's translated into longitudinal model here, where at time point 1 we have a within factor, and time point 2 a within factor, and they are the same. We have the same factor loadings across time, We have the same residual variances across time, equality of those as well. And if you want to study change in factor means, you will have to have the same measurement intercepts across time as well. Now, on the between level then, if you go back up to the multi-level factor model, you have a random intercept for each factor indicator. And there are only 3 of them, so therefore there should be 3 circles here, like it is in the modeling up there, and with 1 factor behind them, and with residuals coming into those U random intercepts as well. And we have equality there as well across time, except that's a sort of a trivial equality because the influence from the U's to the U circles to the U boxes have coefficients 1. So these are all fixed 1, which is sort of an invisible connection here between the random intercepts and the U boxes. They are connected 1, so to speak. So this is then a longitudinal factor model, and if you analyze data in 2-level long format and translate it into single-level wide format and analyzing this model with these equalities, you get exactly the same log likelihood and exactly the same maximum likelihood estimates. Just like we talked about on slide 13, where we discussed a random intercept logistic regression. Except there was a simple case of a univariate response, and now we have 3 response variables and not only 1 random intercept, but actually 3 random intercepts. Now what we cannot do in the multi-level setting here, in standard multi-level factor analysis settings, we can't have any relationship between FW1 and FW2. But once we have moved over to the wide format, we can have this influence. So the model is extended to include, in this case, an autoregression for the FW factors. And you actually have a residual arrow here as well. So that's an interesting longitudinal factor analysis model based on multi-level thinking, and a very rich model where you can tease out within and between sources of variation, where the between sources are now variation across subjects, across individuals, because level 2 is individual and level 1 is time. So this is the within the time factor analysis model. We'll say a little bit more about that in a while. Now if you go back to the cross-sectional setting, what does this influence mean? What would that correspond to? Well, it corresponds to a model where students within schools or perhaps within classrooms influence each other. So you have one student here influencing another. So the students are the within units, right? So that could perhaps be applied in small group research where you have leaders influencing followers. Now this multi-level-based longitudinal model is quite different from the naive longitudinal model, which uses only this bottom part typically, not this top part here with the random intercepts. Now this actually was suggested in a paper that's by Hammaker and others in 2016 in MBR, but it sort of has fallen from the attention of most researchers. It's an argument for having multi-wave data, longitudinal data to decide on factor analysis structures. It's directly based on the multi-level factor analysis model. It's inspired by that and directly translated into the longitudinal framework. And it was called the CUTS model, Common and Unique Traits and States, I think it translates to. So it argues that factors obtained from cross-sectional factor analysis are partly determined by between and partly by within person covariance structure. And that's referring back to work by Cattell in 1978. And that blend of within and between sources is what Raudenbusch and Breich call an uninterpretable blend when you consider multi-level regression. Now, multi-level-based longitudinal factor analysis allows differences between, on the one hand, between person trait-like factor structure, something that's more stable across time, and within person state-like factor structure. So within person state-like factor structure is what you have at the bottom of that model. 2 time points is sufficient to determine the within person factor structure. Typically you would have intensive longitudinal data to be able to estimate a factor model for each person. So we're talking here about n=1 analysis, or Cattell's P technique. So doing a factor analysis for each person where the number of observations then is the number of time points. Of course, then you would need long longitudinal data, which is called intensive longitudinal data. But this article argues that t=2, 2 time points, is sufficient to identify the model on the previous slide. Of course, if you have longer longitudinal data and analyze a group of individuals, you can learn more about your factor structure. And we'll talk about that in a few slides. So this kind of work goes back to work by Carl Jørskog and his longitudinal work with autoregressive models, and Rafalovich, Bornstedt in Sociological Methods and Research, and Herb Marsh together with Grayson wrote about it in 1994 in the DSEM journal. Actually, one of their models is identical to the so-called CUTS model in the Hammacher et al. Article. And Ide wrote about that in 1996, related models, and Domenici-Windel in MBR, and Geiser in Psychological Methods and in Behavioral Research. If you turn to slide 41 then, let's take an application of longitudinal factor analysis done in this multi-level factor analysis inspired modeling framework. So in the Domenici and Windel article, there's an example used also in the Hammacher et al. Article, depression in adolescence, where you consider t=4, 4 time points. And you have 4 items, 4 subscales of the CSD, depressed affect, positive affect, somatic complaints, interpersonal, and you specify 1 factor on both levels, on the within and the between. And then you can consider, for simplicity, just 1 fit comparison measure based on the information criterion BIC, which based on maximum likelihood and rewards models with high likelihood and relatively few parameters. And a low BIC is a good fit, better fit to the data. So for the naive model versus the multi-level-based model, both with AR1, autoregressive lag 1, and again, the naive model, going back to slide 39, is the model that only has the bottom part in it. So for the male sample, the BIC improves drastically from 26,000 down to 25,000. For females, from 32,000 to 31,000. That's quite a big improvement in the model fit. Now, also the naive model gives inflated reliabilities. So these are, 1-factor models, and if you look at the standardized loadings, you can see what the reliabilities are going to be. You can square them, and that's compared to the naive model gives inflated reliabilities relative to what you get in the longitudinal factor analysis model based on multi-level modeling for the within factor. And it also gives inflated autoregressive coefficients, how factors depend on each other over time. Now the question is then, when we are in this rich a longitudinal modeling framework based on the multi-level factor analysis model, we can be interested in various kinds of reliabilities. Reliability with respect to the within factor or the between factor, which is the trait factor, the more stable factor, or both, or some sort of combination of the two. Now, so one can think about this and ask the question, what then does longitudinal factor analysis, this longitudinal factor analysis that's based on multi-level factor analysis, what does it imply for cross-sectional factor analysis of a single time point? And what does it imply for latent class analysis? So what I did was I generated data from a longitudinal factor analysis model with within and between variation, and I analyzed one time point using what I call the regular naive factor analysis. So, for example, I used data generated by one between factor, but where the items had different loadings across indicators. I imagine, for instance, a model for anxiety and depression, where anxiety items have different loadings than depression items because they may vary across individuals differently, different amount of variation as reflected by those loadings. So I have two sets of loadings for this one between factor. And then I have one within factor with equal loadings across the items. Now, regular factor analysis then would mistakenly settle on two factors. There is then a clear two-factor factor loading pattern. But the model that the data were generated by doesn't have variation across individuals in two factors, as the naive analysis says, but instead you have variation in one factor across individuals and variation in one factor across time. So one between factor, one within factor. But they're not two factors that vary across individuals. So you would get the wrong conclusion here. So that says essentially, to use a term from complex survey analysis, we're dealing with a non-aggregatable model. If you generate data by a multi-level factor analysis inspired longitudinal factor analysis model, it is not obviously clear, and most likely not the case, that you would find the same model if you analyze it, ignoring the between part as you would in the cross-sectional regular factor analysis. So this has been seen in other situations in cross-sectional multi-level settings. I wrote about it in 1989 in this paper, and also together with Albert Sartora, we wrote about it in the complex sample data setting. And you may want to take a look at those articles. So now we've reached slide 43, and we can conclude on our modeling part of this web talk. So we've touched on random intercepts in statistics, latent trait in psychology, and measurement non-invariance in psychometrics. So in statistics, we talked about random intercepts in the context of cross-sectional data, where you have variation across clusters such as schools in the measurement of the student factors. In longitudinal data, you have random intercepts that are varying across individuals, and they are constant across time. And that is then very much akin to latent traits in psychology, something that is stable across time, and it's also related to psychometrics, where you have measurement non-invariance as represented by random intercepts. So in some cases, random intercept measurement non-invariance is a nuisance in a way that you want to take into account, model. Sometimes in psychology it's a latent trait which is of primary interest perhaps to study. And in statistics we know that we need to use random intercepts to correctly specify the model in a hierarchical data situation. Now it's time to come back to the multiple indicator latent transition analysis setting with this background. So we have the standard LTA model here with its initial status probabilities, its transition probabilities, and its measurement probabilities. And at this point it is clear what is missing, and that we really should write the model with the help of this figure. 3 time points, 2 measures at each time point, and a random intercept factor f. So in this case then we have loadings lambda 1 and lambda 2 that are held equal across time, where the factor variance is fixed to 1. Now just to remind us, how do we get to this particular model? Let's go back to slide 35 for a second. Slide 35, on the right hand side, you have a latent class variable, and you have random intercepts for the observed categorical outcomes, and you have one factor that influences all of those random intercepts, no residual variances, no residuals added to it, so it's a unidimensional model. And we could just as well then have a connection of U1 and U2 influencing U1 and U2 with etc. with coefficients 1. That's one piece of inspiration. So we want to take this model, the longitudinal, so we want to have C at time 1, C at time 2, etc. So then we borrow from the knowledge that we gained from slide 38. So we start here. This is very much the same as the multi-level LCA model, except in the multi-level LCA latent class analysis we have a categorical latent variable here. So in this case we can go longitudinal and write the model like this. So this would be latent class variable at time 1, latent class variable at time 2, etc. We have measurement invariance across time, and we have a between level factor that influences each of the 3 indicators with coefficient 1 at all time points. In the random intercept LTA model that I'm presenting, we don't have these residual arrows to simplify the model. So going back then to slide 45, you see the model here. We have one between level factor, so to speak. It is a random intercept which influences each of the indicators differently, different lambdas, but influence them the same across time. So in that sense, it is like a trait, latent trait, a stable latent trait. And thereby, we pull out that between subject variation in the observed variables. So what remains is a latent class variable that captures within level variation. And it's the within part that we have an LTA or a transition model for. So this is the paper that's has been under review in Psychological Methods, and the revision of that paper got a good review, and it looks very likely that it's going to be published in that journal. And we have a special website on the Mplus website where you have the Webtalk listed and papers on this, both the so-called final version, it's going to be a little bit different, but the revised version of the paper and the early version of the paper, because the early version has some analysis that were left out. The reviewers didn't want 4 examples, so it got boiled down to 2 examples instead. And you have all the data sets that we're going to talk about in the application section of this Webtalk. You have them here, and you have the different scripts for version 2 of the paper. Now, if you want to find this very easily on your own, you just go to the left margin of the Mplus homepage and you find RI-LTA, Random Intercept LTA. Now, let's take a look at this model and think about it a little bit more. So, one important feature is that it usually fits the data much better than regular LTA. And regular LTA, from this point of view, from the RI-LTA point of view, looks unnecessarily restrictive and gives distorted results. RI-LTA does not confound the between and within subject sources of variation. The influence of the latent class variable at one time point onto the next represents a within subject process, free of time invariant between subject differences, which, as we have discussed, could be seen as trait differences or measurement non-invariance. And we see that the latent class indicators correlate over time beyond what's captured by the latent class correlations over time. So the U variables are not only connected via the latent class variables, but also via the random intercept factor up here. And that tends to reduce the probability of subjects staying in the same class as compared to regular LTA. So lower probabilities on the diagonal of the transition matrix. And it tends to reduce the need for mover-stayer modeling because movers and stayers can be captured by different random intercept values. So if you have a high positive random intercept value here, you may have a consistently high probability for a U equals 1 response as compared to a U equals 0 response. So the random intercept factor captures some of what mover-stayer modeling tries to do, but in a more continuous fashion. Now, because RI-LTA adds a random intercept factor, we add one dimension of numerical integration in maximum likelihood. And that can be, although it's only one dimension of integration, that can be time consuming because the numerical integration needs many random starts in the mixture setting to find the global maximum. So to meet that challenge, we came out with Mplus version 8.4 last November, where significant speed improvements were made for mixture models with multiple latent class variables, so LTA and RI-LTA. And Tiamer and I came up with a new 3-stage random start search, which is much more effective and throws away poor optimization sets based on poor starting values. And Tiamer came up with some nice specialized algorithms inspired by Baum-Welch ideas that we talked about in the hidden Markov setting. And this is described in this technical report, which you find on the website as well. It sits here, and it has some nice discussions and a timing table which you might be interested in studying. I'll just give you an excerpt. A 20 hours computation in Mplus 8.3 can be done in Mplus 8.4 in less than 15 minutes by utilizing these combined advantages, including going to an i9 Intel processor instead of typical i7s or i5s. Much faster. And we also made substantial simplification of the output for mixture models with multiple latent class variables. So LTA analysis is a little easier to handle. As an aside, on slide 48, I should mention that all the way through here, I've been talking about continuous normal random effects. So that's the main model used also in Mutena-Sparahov. And of course, that's a main model used in multi-level modeling too. But there are alternatives, discrete approaches to describing the random effects have been used. So it's called non-parametric. So you can have, say, 3 different categories where the distribution can be quite skewed. The leftmost category can have a lot of individuals in it, and the rightmost very little, instead of having a symmetric distribution. So that translates into having one extra latent class variable in the LTA setting, or in the RI-LTA setting. That's been proposed in the context of latent trait modeling by Eid and Lange, and in an article that uses the data that I'm going to use later on in the mood data. 2 articles actually. But it's also been used in the random effects setting for hidden Markov models. Maruotti has a International Statistical Review article on mixed hidden Markov models, including discrete random effects. And a book by Bertolucci and others describe such discrete random effect modeling as well. And in this paper, in the RI-LTA paper, a discrete alternative using a binary random effects variable is presented, and it's based on the parameterization in Michael Eid's and Lange parameterization. It is actually somewhat less time consuming than the continuous RI-LTA model, but it gave a worse BIC than the continuous normal model in all applications. More than 2 categories was not needed, so the non-normality aspect of the random effect didn't seem to need to be addressed in these data. But the applications that I'm going to show you next are going to all be based on the continuous normal situation, but the paper also gives a model fit for the binary random effect situation. So turning to slide 49, we have the outline here again. So after all of these discussions of modeling ideas, we're now turning to focus on applications of latent transition analysis and also the new random intercept latent transition analysis. And we're going to do that in the context of 3 different data sets, and those data differ in terms of the number of time points, the sample sizes, the number of indicators per time point, and the number of classes. And at the end of this, we're going to discuss whether or not LTA is the right type of model, or are we fishing in the wrong pond. Just to remind you of the RI-LTA, take a look at slide 45 again. So at the bottom of this slide, if you look at the boxes and the circles at the bottom, we have the regular LTA. And if we include the top part as well, then we have the RI-LTA. So we have a random intercept factor that influences each item equally across time, but different items have different factor loadings. Now, as an aside, we could have had a slightly more general model by having a random intercept latent variable for each of the indicators per time point, influencing the indicators equally across time. So that would be 2 dimensions of integration in maximum likelihood terms. And it seems like for the data that I've looked at, that you don't need to go beyond this single random intercept factor, a single dimension. But you could, and it's, however, impractical when you get many more indicators. The number of dimensions increase beyond what you can handle easily by maximum likelihood. And Bayesian analysis in this mixture context can be quite tricky to carry out. Now, the first observation we make is on slide 50, the fact that the fit is typically much worse for regular LTA than RI-LTA. In the first paper, in the first version of the paper, we analyzed 4 different data sets: life satisfaction, mood, reading proficiency, and dating. In the second version, we only work with mood and dating. Here we will talk about reading as well, but we'll do a more thorough analysis of those data than we did in the first version of the paper. This life satisfaction example comes from a chapter contribution by Lange and Van der Poel in 2002 in the very nice applied latent class analysis book edited by Hagenars and McCutcheon. That reference is given on slide 4. So what you're looking at here then is the number of parameters, the log likelihood, and the BIC, the BIC, where BIC is scaled so that lower values are better. So BIC tries to measure how good the likelihood is, but giving a penalty for using many parameters. So you want a parsimonious and model that fits the data, or where the likelihood is high, so you're closer to the data. And in any case that you look at here, the BIC improves radically. It drops quite a lot, 30,745 to 30,637. And same for the mood data, 4150 to 4093, 4380, etc. Big drops. The log likelihood is also given. Now, you should notice then that what we have here is the difference in number of parameters in any case here is the number of indicators per time point. Here we have 1 indicator per time point. By the way, here's a typo. It should say j equals 2, 2 being the number of classes. Here we have 2 indicators per time point, so we have 2 parameter difference, 5 here, and 3 here. Now in terms of testing whether or not the RI-LTA is necessary, that's a little difficult because we get into testing when the new model adds a variance component, the random intercept factor. So that's a tricky topic. You can work with mixtures of chi-square distributions, but it's not clear exactly how you would apply that to this situation. So I'm going to leave that aside. Nevertheless, we're going to note that, like here, there's a huge difference in the log likelihood here, which if you did the regular 2 times log likelihood difference test, it would be a very large number relative to only adding 1 parameter, that is a 1 degree of freedom test. It's going to be sufficient for us to look at BIC alone, given these large drops improvements in BIC. So let's take a look at our first data set then, which is the mood data. So this comes from an article by Eid and Lange, and it draws some data from a German multidimensional mood questionnaire. So here we have a rather low sample size of only around 500 observations, which is low in LTA settings. You really want a couple of thousand. And here the individuals are measured 4 time points, as I mentioned, and 3 weeks apart. We have 2 binary items based on ratings of momentary sadness and unhappiness. We're going to work with a stationary model, which means that we're going to assume that the transition probabilities are equal across time. That's a simplification of the model that quite often fits quite well and certainly simplifies the interpretations. So this comes from this article, 2003. And just repeating then again, the model fit here in terms of log likelihood and BIC, regular LTA, 7 parameters, and RI-LTA adds 2 parameters, 1 for each of the 2 indicators per time point, so the 2 factor loadings. And we see this substantial improvement in BIC. So then let's take a look at interpreting this model for both the regular LTA up here and the RI-LTA. And as we did with the dating example in the first early segment, I think it's segment number 2, we will start with interpreting the measurements. That is, looking at the measurement probability pattern to understand what the classes mean. So the column here are the classes, 2 classes. We're going to call them high mood and low mood. We have the indicators sad and unhappy, so they're binary. U equals 1 means that you're sad, U equals 0 means that you're not sad. Same for unhappy. And you see then that if you're in a low mood, you have a very high probability of endorsing the sadness item, of saying that you're sad. That is U equals 1. And you also have a high probability of saying that you're unhappy. If you are in the high mood class, if you classify as a high mood person, then you will have a much lower probability of saying that you're sad and unhappy. It's not 0, so it's not perfect measurement. You can think of this as a measurement error of sort, either by people carelessly answering or interpreting the sadness and unhappiness items slightly differently. Now, if you compare that to what we get from RI-LTA, you get a little bit of a different picture. You get less discrimination between the probabilities here, the high mood and low mood columns. That is, these probabilities are a little bit higher, less close to 0 than they were for the regular LTA. So in a sense, this measurement model gives an impression of the items measuring the mood much better than what they do down here. Now, that's not a reason for choosing a regular LTA, because if this is the true case of affairs, as the better model fit indicates, then this would be a distorted view of, a wrong impression of good measurement. And then the second part of interpreting the LTA is looking at the transition probability estimates. So here we have, again, high mood, low mood, and the classes, the rows are also high mood, low mood. So for regular LTA, we have a fairly high probability of staying in a high mood from 1 week to 3 weeks later. Same for those who start in the low mood. They're very likely to stay in the low mood. Now with the RI-LTA, it's quite different. You have a higher off-diagonal probability, therefore a lower diagonal probability, and particularly so for those individuals who start in a low mood class. They're almost equally likely to stay in the low mood as they are to move to a high mood. And that's quite different. That second line is quite different from the second line for regular LTA. And it remains to be seen if that is a common type of outcome, but it is the case that it is quite likely that the RI-LTA lowers the diagonal elements of the transition matrix, as it does in this case. Now, if you expand the model, we looked at the top part before. If you expand the model from the standard LTA situation, be it regular LTA or RI-LTA, to including a mover-stayer latent class variable, a binary latent class variable, where we try to figure out if you can identify movers and stayers, where stayers are those who have probability 1 of staying in the same class and probability 0 of transitioning to other classes. So if you take a look at regular LTA here, and you adding then one parameter, going from 7 to 8, that's the probability for being in the mover class or stayer class. And the BIC improves quite a lot, 4150 to 4123. So if you use the regular LTA, you would conclude that you should have a mover-stayer model, not just a standard LTA model. Now if you look at RI-LTA, It also adds one parameter, but BIC does not improve. In fact, it gets a little bit worse. So with RI-LTA, you would tend to stay with the RI-LTA standard model up here, which is still better in terms of BIC than the mover-stayer regular LTA here. So that's what I summarize in the first bullet at the bottom here. And there is perhaps a general feature here that when you use this random intercept factor, that you have less of a need to add a mover-stayer component to your model, because the factor values, the factor scores for the random intercept factor can to some extent capture stayers. For instance, if you have positive factor loadings, a high factor value in this case would tend to say that you are likely to answer in the sad and unhappy categories at all time points, remembering that the factor is really like a trait, or is a trait that is something that is time invariant. So if you have a high positive factor score, that will tend to say that you're more like a stayer. So this is a continuous version of the binary mover-stayer model that you achieve by adding this random intercept factor. On slide 56, we take a look at the second example, transitions in dating and sexual risk behavior, from the 2008 developmental psychology article. We talked about this data set earlier in segment 2 on slides 5 to 7, and just a repetition here, the data come from NLSY 97, about 3,000 subjects, 3 time points 1 year apart for individuals aged 17 to 18 when they started. And we have 3 items. The first item is ordinal with 3 categories. Second item is ordinal with 3 categories. And the third item is binary, exposed to sexually transmitted diseases, yes or no. So we're going to take a closer look at this data set and contrast the regular LTA analysis with RI-LTA. So regular LTA, then 49 parameters. RI-LTA has 52 parameters, 3 more for the 3 loadings for the random intercept factor. A substantial improvement in the log likelihood. This is much better, much higher. And a substantial improvement in BIC, almost 32,800 going down to 32,500. A very big drop. And the RI-LTA also finds 5 classes as being the best choice, but only the non-daters and daters and multi-partner exposed classes from the regular LTA are found in the RI-LTA. Instead, we find 2 different classes. One class with individuals who are monogamous with respect to the sex partner, but who has multiple dating partners, whereas for regular LTA, the monogamous person was having 1 sex partner, but also 1 dating partner. And then we find a class that could perhaps best be described as being monogamous, but exposed, that is, exposed to sexually transmitted diseases. And here at the bottom, you see the transition matrix. So you can compare that matrix to the one that we presented on slide 7 using regular LTA. And you see, by and large, that we have more substantial off-diagonal probability elements for daters here, moving from non-dater to dater, and here moving from monogamous to monogamous exposed and to multi-partner exposed. And for the monogamous exposed category, we have a non-ignorable probability of moving to the multi-exposed class. So somewhat different conclusions by a model that fits the data considerably better. Going forward then, like we did for the mood data, we move into taking a look at what happens when you add a mover-stayer component. So that's this bottom part of the table. So for regular LTA, again adding one parameter for the probability of being a mover or the probability of being a stayer, whichever you like to consider. You have BIC going from this value to this value, a considerable improvement, and you would choose the mover-stayer model for the dating data, not the model that we just described. For RI-LTA, you have this BIC value, and you get a worse BIC value when you add RI-LTA. Not that much worse, but why choose that model since it's less parsimonious? The RI-LTA has a better BIC than the regular LTA that includes mover-stayer by far. So again, RI-LTA wins. And here again, as for the mood data, we pointed out that RI-LTA allows a continuum of staying instead of the stayer class. The RI-LTA model captures staying also via different random intercept factor values. You can actually take a look at the data and see who are the stayers and compute the estimated factor scores for those to verify that the intercept factor values are either very low or very high. So RI-LTA does not need a stayer class, but if you add a stayer class, as we did on the previous slide here, adding a stayer class, if you do that, you get 9% stayers, whereas with regular LTA, you get 20% stayers. So the two models disagree there as well. And like we said, regular LTA with a mover-stayer component fits the data considerably worse than the RI-LTA model with a mover-stayer component. Now RI-LTA, since it has more parameters, it makes it possible to also learn more about the indicators. The estimated RI-LTA intercept factor loadings, in this case, they're all significant and positive, are as follows for the three items, where you see that the number of sex partners has the largest factor loadings. So it's the strongest indicator of the random intercept factor, that is this time invariant trait. So in terms of stable, across time stable traits, number of sex partners is the key indicator. On slide 60, we're going to take a look at the third example for comparing regular LTA with RI-LTA. So it has to do with reading proficiency, where we're going to study data from the early childhood longitudinal study with a nice sized sample of about 3,600 children, measured at 4 time points, fall and spring of kindergarten and fall and spring of grade 1. We're going to consider 5 binary items measured at each time point, and they represent a stage sequential process with mastery of these 5 domains of reading development. We're going to consider 3 latent classes corresponding to 3 stages of learning, as found by David Kaplan in his Developmental Psych article, and as we also found when we used RI-LTA, 3 classes. Slide 61 then shows the 2 models competing. The RI-LTA model has 5 more parameters. These are the 5 random intercept factor loadings corresponding to the 5 latent class indicators, the 5 items that we measure at each time point. BIC is about 44,000 for regular LTA, but drops dramatically down to about 41,000 for RI-LTA. So a model that is much closer to the data. On slide 62, we see the reading data measurement probability patterns that we use to interpret the classes. They're given these names by Kaplan's article: low alphabet knowledge, early word reading, early reading comprehension. We're going to compare regular LTA with RI-LTA as usual. So if you are in the low alphabet knowledge class, you have essentially 0 or very low probabilities of mastery for all items except for letter recognition. But you only have like a 51% chance of mastering that item, that domain, even in the low alphabet knowledge class. Going to the second class, the probabilities of mastery increase dramatically, and although you have essentially 0 probability of mastering the last two, sight words and words in context. And the highest class then has almost probability 1 of mastery, except for words in context, where there's a 51% chance of mastery. Going to the RI-LTA, we see a similar pattern. Low probabilities rather, at the bottom here. We have a little bit higher probability, 0.303, for beginning sounds in class 1 than we do for regular LTA. And we also have a little bit higher probability for sight words than what we have in the regular LTA. And substantive experts have to decide whether or not that's a reasonable outcome. But by and large, the pattern of probabilities is similar and would lead to very similar interpretations of the classes. Now here's a display that we haven't looked at for the previous two data sets, looking at the latent class probabilities, or the latent class proportions. So for each class, each of the 3 classes, at the 4 different time points. So in the fall of kindergarten, 69% are in the lowest class, 28 in the middle class, and only 2 in the highest class. So this adds up to 1 here. And in spring of kindergarten, we still have 24% in the lowest class. If you compare that to RI-LTA, you have a more optimistic picture, perhaps, in the sense that the proportion of kids in the lowest class in spring of kindergarten is lower than it is for regular LTA. So we don't have as many kids in that low class anymore. With the thinking is that these kids, there should be fewer people here if the reading development has gone well. Same thing here, a lower proportion in the low class as judged by RI-LTA when you compare it to regular LTA. Still 14% in the lowest class in fall of first grade. On the other hand, you have a less optimistic picture here for RI-LTA, for the bottom class, where you have 8% in the high class in fall of first grade, as judged by RI-LTA, but you have 23% in that high class in fall of first grade. So some kids are in that best class already in fall of first grade, as judged by regular LTA, but far fewer are in that class, high class, already in fall of first grade. So this is how you can think about the class probabilities, class proportions, and how you can compare the different models. Slide 64, you have the more familiar transition probabilities as judged by regular LTA and random intercept LTA. So we have the 3 classes as both rows and columns. And here we consider 2 transitions. One is from fall kindergarten to spring kindergarten, and the other is from spring kindergarten to fall of first. The third transition from fall of first to spring of first is not presented here. So for instance then, as judged by regular LTA, you have a probability 338 of staying in the low class from fall to spring in kindergarten, but a good probability of moving on to class 2. Now if you compare that to RI-LTA, you have a more optimistic picture here because you have a lower probability of staying in the low class than regular LTA and a higher probability of moving on to the second class than for regular LTA. Same thing in the transition from spring kindergarten to fall first. You have a lower probability of staying in that low class, higher probability of transitioning up than for regular LTA. So slightly different results here for the two models. Slide 65, I want to take a little time to penetrate the interpretation of this new RI-LTA model. The new thing is, of course, the random intercept factor up here. And what does that mean? I'm going to try to put that in a measurement non-invariance perspective. So once again, we look at this, say, binary latent class indicator. You are one of the many. Individual I time t and in a specific class C. And we look at the logit for probability of u equals 1 once again. And then now we're going to condition on two things. The latent class, so the class variable is equal to a specific latent class, the lowercase letter here, and a specific factor value sub I for individual I. And it's a logit regression, and we regress on the factor. And we have a slope, lambda, loading, and an intercept. Instead of an intercept, we use a threshold in the Mplus notation because it's more general, can deal with ordinal variables. And the threshold is the negative of the intercept, so we write it with a negative sign. So this is tau for the threshold for item R in class C. So it varies with classes and varies with the items. And then we have the loading, which varies with the item, but not with the classes for this model, multiplied by the factor value. A high logit implies a high probability of u equals 1, as we've said before, and that occurs for a positive loading and a factor value that's greater than 0. So with a positive loading, the higher the factor value, the higher the probability of answering u equals 1. Now in the previous presentations of measurement probabilities, the random intercept factor was integrated out. So we didn't condition on F, we only conditioned on C. That is, we looked at this expression. That's the overall conditional probability that we consider in regular LTA. But if you condition on the factor value as well, you can then see that individuals with different factor values have different conditional probabilities. We have a contribution lambda times F as shown in equation 21. So F is something that varies across people but not across time. It means that the random intercept factor can be seen as capturing measurement non-invariance. Now, applying that to the reading data, we can look at the measurement probabilities one more time. At the top, you have what we looked at before, the overall probabilities. But at the bottom, we now look at two different F values, F minus 0.5 and F plus 0.5. So one standard deviation apart, the mean of F is 0. And you can then see that the probabilities of mastery on the left are lower than those on the right, as you would expect, according to the previous slide discussion. And interesting signs also that these probabilities at the bottom are lower. What I mean is that the probability of mastering beginning sounds is lower than the overall, for the overall probability assessment. And also the probability for sight words is lower than for the overall up here. And the probability for words in context is lower than for the overall assessment up here. The reason I'm emphasizing that is that because we can look at this on slide 67 relative to a measurement of poverty. So at the top, we once again repeat what we had at the bottom of the previous slide. And at the bottom, we do a new kind of RI-LTA, which allows for measurement non-invariance across poverty groups. So this can be done by a multiple group analysis. And there are 19% in the poverty group and 81% in the non-poverty group. So these are observed groups. We do multiple group analysis. And you see then again that the probabilities are smaller for mastery over on the left than on the right. And we have the same pattern for poverty as you have for pretty much f equals minus 0.5. Very similar pattern of probabilities as you do for the poverty group. And if you relate the random intercept factor to poverty, we can see in the regression that they're strongly related to each other. So you can investigate measurement invariance in this way by looking at different factor values, but you can also make it more real by relating the factor to an observed background variable, such as poverty here. And we're saying then that the random intercept factor can perhaps be viewed as a reading preparedness dimension, strongly related to poverty. And it's a quite different probabilities here for letter recognition in the poverty group as compared to letter recognition in the non-poverty group. And those probabilities are substantial also for several other of the items. Okay, we'll stop there, and we'll come back to the reading data in the next segment and take a further closer look at the reading data interpretations. On slide 68, we turn to model variations on the random intercept latent transition analysis theme. And there are many such model variations and model extensions that are possible in the framework that Mplus provides. For instance, standard LTA typically assumes and works with only lag1 models for the latent class variables. So if you have 3 time points, the latent class variable at time 2, C2, is regressed on C1, C3 is regressed on C2, but C3 is not regressed on C1. It is quite possible to add lag2 and even lag3, etc. for these variables. And in fact, for these data, there was significant evidence for a lag2. We can do a likelihood ratio chi-square difference test and find that to be significant. So that could be explored to see how much adding to the model, making it more general, changes the interpretations, changes the results and the transition probabilities. There was also some evidence for correlated residuals for the categorical indicators across time. Such residuals are possible to add for these models, and one can also explore how much adding such residuals when they are significant changes the interpretation. You can also add distal outcomes, that is some variable that is somehow predicted by what goes before it in the LTA model, either probably mostly then in terms of the latent classes and probably mostly in terms of the latent class status at the end of the process. You can also add time trends for this kind of a model. That is, we've talked about the random intercept, but we can also add a random slope, or at least a fixed slope, to allow for a time trend. I investigated that and only found evidence for the need of this for the reading data, where there is a natural upward trajectory in terms of reading achievement. And in this general framework, we can also work with multiple processes, that is more than one LTA going forward, and we can actually have processes that have cross-lagged influence, so a cross-lagged RI-LTA in line with the RI cross-lag panel model, RI-CLPM model. And of course you can add to this multi-level RI-LTA. That is, you have time within individuals and then individuals within clusters such as schools or communities. That's a feature that we have not added here yet into Mplus. One key question though is if these LTA extensions are sufficient to capture the essential parts of the data. Is LTA the right type of model? Are we fishing in the right pond, so to speak? And you may particularly focus on whether or not classes or dimensions should be included, should be the dominating description of the data. So we can, from this perspective, we can contrast latent transition analysis and the longitudinal factor analysis that we talked about in previous segments. Now, longitudinal factor analysis has many continuous latent variables, many factors, which typically leads then to high dimensional integration for maximum likelihood, because we have categorical outcomes. That can be heavy for ML, but it could be very easy for Bayesian analysis. Now for LFA, longitudinal factor analysis, the number of dimensions turn out to be the number of time points times the number of within factors plus the number of indicators. So if you look at the model at the bottom here, we have 2 time points, t equals 2. We have 1 within factor, so t times 1. So 2 times 1 plus the number of indicators, 3. 2 plus 3 is 5 dimensions of integration for ML. It's doable, but a little bit heavy. For the MU data, we have 4 time points, 1 within factor, 2 indicators, so that turns out to be a 6-dimensional integration. For the dating data, we have 3 time points, 3 indicators, so it's 6 dimensions again. And for the reading data, we have 4 time points and 5 indicators per time point, so it turns out to be 9 dimensions of integration. Now, I actually tried this and contrasted the findings, the model fit values from LTA with LFA using maximum likelihood. I could have done this using Bayesian analysis also, but I wanted to relate the results back to the ML log likelihood and BIC values we got for the mixture modeling of RI-LTA. You could do Bayesian RI-LTA as well and then compare and do Bayesian analysis for all models, and then you can compare the so-called PPP values. But here we go with ML. So for the MU data, RI-LTA has 9 parameters, and this log likelihood and this BIC value. For the factor analysis, so no mixtures, we have 16 parameters, 7 more parameters. The log likelihood is a little bit better. However, we cannot do a chi-square difference likelihood ratio test here, because we have a mixture model in one case and we have a non-mixture model in the other case, and we have different number of random effects in the model. So the naive chi-square difference test would probably be wrong. This is a little bit better likelihood, but is it worth it by adding 7 more parameters is the question. And I think BIC is the best measure to answer that. And it turns out that BIC gets worse for LFA. So here, for the mood data, we could be satisfied with staying with RI-LTA. For the dating data, the LFA has considerably fewer parameters, but it also has a worse log likelihood value. And you see that you're then punished for the worse log likelihood value despite having fewer parameters, in that BIC is considerably worse than the RI-LTA BIC. So I bold the best BIC values here. So for both the mood data and the dating data, we go with the RI-LTA model and not the LFA model. Now for the reading data, RI-LTA has 40 parameters, LFA has 29 parameters, so considerably fewer parameters. But lo and behold, the log likelihood is better for LFA than RI-LTA, even though we have fewer parameters. So clearly then BIC is going to win. You have a much smaller, much better BIC for longitudinal factor analysis. So you should not go with this RI-LTA model that I talked about. In this case, you should go with longitudinal factor analysis. Turns out that I should mention though that this is 9-dimensional integration, so the log likelihood value is a little bit difficult to pinpoint exactly. But it's probably close enough so that the better BIC value is a trustworthy indication of a better model. Now for the LFA, you can look at then the indicator variances, the random intercept variances, which reflect the measurement non-invariance across individuals for the 5 different binary indicators. So letter recognition has a large variance component relative to beginning sounds and ending letter sounds and sight words, whereas words in context is also having a large variance component. So a large degree of measurement non-invariance for the first and the last indicator. So then you can speculate about that substantively. Why does that happen? Does it have anything to do with the fact that letter recognition is the first reading domain that you master and words in context is the last domain? You can investigate that and think about that. And in this model, actually, in this longitudinal factor analysis model, I bring in the means or thresholds. That is, I have threshold invariance across time and allow factor means to change and factor variances to change across time. And you find then that the factor means increase significantly, except between spring, kindergarten, and fall of first grade. Maybe then reflecting that well-known summer drop problem. So more generally then, this raises an important question. Can we use a model that fits much worse than another model? So that is, can we use, for instance, this reading data RI-LTA when we know that there's a much better model, longitudinal factor analysis? Well, that's an interesting question. And the immediate answer would be no, you shouldn't use RI-LTA when you know about this model fitting so much better. But is there any part of the RI-LTA conclusions that are useful? Can the model be used for some purposes? For which purposes can it be used? And you can also ask, what if you fit an LFA model which fits the data much better, and then try to extract the type of information that you were interested in when you formulated the RI-LTA? That is, work with a continuous latent variable model, but try to deduce implications in terms of latent classes. Is that possible? That's a question you can ask yourself. Now, you would also say then that none of these models probably fit the data that well. In fact, you could take a look at the reading data. There are 5 binary indicators at 4 time points. That's a lot of cells in the frequency, in the multi-wave frequency table. And you can look, for instance, at bivariate model fit statistics, such as those given by Mplus in Tech 10. And you will find that there are many significant deviations from good fit in those bivariate cells. Of course, it's very hard to look at the overall chi-square test based on a frequency table because so many of the cells are going to be empty. So there's always the risk that even this better LFA model is not good enough. That is, it is misfitting. That is, you can find better models than this for the data. So here's a challenge to you, the listener. How would you improve on this modeling? What modifications will you make to make it fit better? And if you find such a better model, is it going to be changing the conclusions that you made based on the LFA model? On slide 71, we come back to the outline. We have now gone through the modeling ideas and gone through the applications of latent transition analysis. And we are now turning to multi-level time series analysis, which we call DSEM, or dynamic structural location modeling. So now we turn to the vice versa of the title and asking the reverse question: what can single level modeling teach us about multi-level modeling? What you see here then is the picture for single level modeling using the RI-LTA model for 3 time points. So now we ask ourselves the question: how do you analyze relationships between variables at different time points using 2-level modeling? So here we have 3 different time points, and we have relationships between the latent class variables here. How on earth do you do that in 2-level modeling? It's not naturally set up to do that. Well, you can do that by turning to the relatively new technique of multi-level time series analysis. So not the old time series analysis that only considers one unit across time, such as SMOG in LA. It's only one LA. But instead look at many units, so many individuals in our case, not just one individual. So multi-level in the sense of time being level 1 and individual being level 2. How do you analyze relationships between variables at these different time points? Well, it becomes easy to do in the multi-level time series framework that we've implemented in Mplus, as you will see. And it has the advantage that you can add new types of random effects, not only these random intercepts for the indicators, but you can add random slopes, random variances, random ordered regressions, that is the relationships between the latent classes here, and random transition probabilities in general. The caveat is that you need many more time points than usually is available in LTA. So with 3 time points, there's not much of that you can do. You may have to have it more than 10, preferably 20, 50 time points. But that is actually corresponding to a type of design of data gathering called intensive longitudinal data, with these different data collection approaches called EMA, ecological momentary assessments, ESM, experience sampling methods, and daily diaries. So here's dynamic structural equation modeling in a nutshell on slide 73. Starting with a single level wide model, the RI-LTA that we looked at before, we can then rewrite that as done on the right in a two-level long format time series setting. So we have then the regression of C, the latent class variable at time t, on the latent class variable at time t minus 1. And it goes back ... here and goes forward ... here. And at each time point we have two indicators corresponding to the two indicators that we have in the picture on the left. So that's U1 and U2 at time t, and here time is 1, 2, 3. And then for those indicators we have random intercepts, and we choose to model that on between for the variation across subjects using one factor that influences each of the indicators with different loadings. Factor variance fixed at 1 here. We don't have any residual arrows here to reduce the dimension down to 1 to make this correspond to the drawing on the left, where we also have only one dimension, not any indicator specific random intercepts. So DSEM data are in long format. It's a two-level model and data are in long format. So the two outcomes per time point that we have here results in only two columns of data, U1 and U2. Not 2 times t, like here. T is 3, so not 6 columns in the data, but 2 columns in the data. So how do you specify the relationships between variables across time? This relationship here. Well, you specify that by using a lag notation. C on C with lag 1. That says exactly the same as the figure. So that general language makes it very convenient to work with two-level models for time series data where you allow for relationships between variables at different time points. Turning to the factor analysis setting, so corresponding to longitudinal factor analysis, we have what's called dynamic factor analysis then, a special case of dynamic structural equation modeling. So you have a within factor measured by 3 indicators, random intercepts, and in this case you have 3 random intercepts. You have a factor behind them, but you also have indicator specific residuals here. And you regress the within part on the previous factor value. So this is the within person factor structure that we're looking at. You know, that corresponds to Cattell's P technique, where he does an analysis for one individual at a time, in this case for 3 variables with the number of observations equal to the number of time points. Here we have added a second random effect, namely the autoregressive coefficient phi has a filled circle which becomes an open circle, a continuous latent variable on the between level. That's correlated with the factor on the between level. And again, as usual, we can regress these factors on predictors, and they can also predict other variables, distal outcomes on the between level. An example of this is an example that Timur Asparov and I have used in several of our papers on our website. It has to do with affective instability in EMA data. And it's in this article from 2008 in Psych Methods by Yang, Wood, Trull. And thanks to Phil Wood, we have gotten access to these data. It's an example of this growing amount of EMA intensive longitudinal data. N is only equal to 84, where 46 outpatients meeting borderline personality disorder and some meeting major, you know what I mean. Each individual is measured several times a day for 4 weeks, so it gives a total of 100 assessments. So even though we have only n equals 84, we have t equals 100. And the authors hypothesize a single mood factor for each individual, which is measured by 21 self-rated continuous items. Actually, an exploratory analysis discovers 3 well-defined factors in the analysis that I have done. And here you have the research question at the bottom. But I just want to show you this as an example that you can do factor analysis for a fairly small number of subjects when you have many more many more time points. So turning to slide 76 then, the 2-level analysis allows for random effects varying across subjects. So as I mentioned, you can have random intercepts, you can have a random autoregressive coefficient, you can have a random residual variance here, and we also allow cross-classified analysis, so cross-classifying time and subject. So just having time and subject components contributing to the outcomes. And then you get to have even more random effects varying across subjects and time. And you can also handle random loadings in the DSEM settings. So this is described in the 2 major theory papers. The first one came out in 2017, Dynamic Latent Class Analysis, and the second one in 18, Dynamic Structural Equation Model. So the dynamic latent class analysis corresponds to having latent categorical variables, so latent class variables. We have software for doing some models of this, but we have not released that software yet because we haven't seen a strong need from users asking for it. But if the requests come in, then we will complete that software development. The software development is done for this, dynamic structural equation models, that is when you have continuous latent variables. The observed variables can be categorical as well as continuous. This development is described on the special page time series analysis. You know, we have these special Mplus topic pages in the left margin. So we have time series analysis, DSEM. And that's the page we're looking at here. And it started with Mplus version 8 from April 2017. DSEM theory, and there's also RDSEM, residual DSEM, which is quite interesting, and then we're about to write more papers about. So here you have the 2 key theory papers, but since then Tiermer has also taken the lead in writing a centering paper related to this, and a paper comparing various models for intensive longitudinal data. And there's a series of DSEM application papers listed here, and workshops. The 2017 Johns Hopkins workshop, where we spent 2 days on DSEM modeling, we being me, Tiermer, Ellen Hamaker, and Morten Schultzberg. So here you have all of that information to study. And now we turn to the end of this web talk. On slide 77, we have a so-called Appendix A, where we talk about sample size requirements. And it is the case that when you consider latent transition analysis, you typically need very large samples. You should have at least over 1,000 observations, I think. Because if you want to be studying transition probabilities, you don't want to have too large standard errors to be able to say something specific about them. So a couple of thousand observations preferably. You saw sample sizes that went up to 3,000 and even 5,000. And that's good. Now when it comes to random intercept LTA, I studied the requirements for sample sizes there in a small Monte Carlo simulation study in the second version of the Martinez-Barahov paper. I looked at latent class indicators that were binary, and I looked at different number of time points. And I found that when you have at least 3 time points, you get good performance at sample sizes of at least 1000. That is, you get good parameter estimation, not too much bias. You get good standard errors, that is, agreement between the empirical variation in the parameter estimates and these average standard errors, and you get good coverage. But with only 2 time points, you really need more than 4,000 subjects. So in that sense, RI-LTA needs larger samples than regular LTA. Regular LTA can work well with only a couple of hundred observations. Now this is something I studied when I generated the data by each model. So each model is correct. So when I generate a regular LTA model and analyze it by regular LTA model, it works quite well at much smaller samples than when I generate data by RI-LTA and analyze it by RI-LTA. But that's small comfort for regular LTA, because if data had been generated by RI-LTA, RI-LTA estimates are much better than the regular LTA estimates at sample sizes as low as n equals 500. And we have seen now in several real data analysis that RI-LTA is more likely to have generated the data than regular LTA. And if that's true, then the distortion in regular LTA estimates is bigger than the deficiency of the RI-LTA estimation at sample sizes as low as 500. So RI-LTA is quite practical in terms of realistic sized samples. Now when it comes to decent dynamic structural equation modeling or multi-level time series analysis, Schultzberg and I wrote a paper in 2018 in the DSEM journal about the number of subjects and time points that are needed to get good results. So that's a fairly large simulation study with models varying in complexity, varying in the number of random effects that you bring in. And for very minimal models with, say, only random intercepts, the estimation works well when you have at least 10 time points for not too large samples. But if you want to have more random effects, random autoregressive features, random residual variances, you need at least 20 to 50 probably time points. And the more complicated the model is, the more random effects, the higher the requirement on the number of time points. Now when it comes to computing time here, discussed on slide 78, Appendix B, that is the concern that we mentioned earlier, that RI-LTA is considerably slower than regular LTA. So here we have some timings using different Intel CPUs and 4 columns. Here's my current computer, an i7 7700, and I contrasted regular LTA with RI-LTA for that. But we also looked at an i9 computer that my colleague has, and I hope to get soon, using RI-LTA with 8 processors and RI-LTA with 12 processors. So for the mood data, which has about 500 observations and only 2 classes, 4 time points, it takes 4 seconds on my current computer using regular LTA. 3 times longer, but still only 12 seconds, so ignorable, using RI-LTA. But for the dating data, where you have about 3,000 observations, while it takes 41 seconds for regular LTA, it takes 6 minutes for RI-LTA. Still practical, but if you get an i9 machine, you can do it in 3.5 minutes, almost cutting the time in half. In that case, increasing the number of processors doesn't help much. For the same dating data, bringing in the 4 covariates that are available with this data set, Takes 5 minutes with regular LTA, 40 minutes, 8 times more with RI-LTA on my current machine. But the i9 machine does it in almost half the time, 21 minutes, and then you get 2 minutes savings by going to 12 processors. Now, Appendix C, the new Mplus features in Mplus version 8.3 and 8.4. I just want to remind you of what they are. 2 versions of Mplus came out in 2019, in the spring and in the fall, 8.3, 8.4. And if you want to catch up on the latest development and additions in Mplus, if you haven't used it in a while, for instance, you can always go to the version history page here, Mplus version history, where we describe carefully the key developments of each release, 8.4, 8.3, all the way down to the first version, Mplus version 1 rather, in November 1998, 22 years ago. So in the last year's Mplus developments, we added mixture modeling features that I have alluded to before, with significant speed improvements for mixture models with multiple latent class variables, which are more computationally demanding. So that's very handy for latent transition analysis and random intercept latent transition analysis. And like we said earlier, the output has been substantially simplified for cases with multiple latent class variables. Now, Bayesian analysis is also quite relevant here, and we have made significant speed improvements for Bayesian computations using this new parallelized computing approach, which recommendation is to say processors equal 8 to get faster computations to benefit from that development. And we have also made Bayesian estimation of 2-level models with latent variable interactions using the X-width option. So we have a Bayesian alternative to ML, because ML gets into too high-dimensional integration to handle that for realistic size models. And Bayesian fit statistics have been added in 3 areas: improved posterior predictive p-values when they're missing data, and Bayesian versions of CFI, TLI, and RMSEA, including confidence intervals, which you get easily through Bayes, and a Bayesian version, and this is interesting, Bayesian version of the wall test that you have in model test for ML. It's a Bayesian version of that to test parameter restriction. So that's a way of testing nested models, restricting a number of parameters to see if they are really necessary. Finally, then on slide 80, I just listed the recent Mplus related papers that we've been relating to. This paper is a technical report that's on our website. It has to do with the improvement in maximum likelihood mixture modeling, speed, and then the Bayes improvement in time, the parallel computations, they're described in this technical report. And then a couple of new papers. This is Bayesian estimation with latent variable interactions that I just mentioned. It's coming out in structural equation modeling. And then advances in Bayesian model fit evaluation, also coming out in structural equation modeling. And the paper that's already come out last year, latent variable centering, that is how you can do better than centering by observed group means, and instead do latent variable centering, even in multi-level and in time series models. And another general paper comparing different kinds of models for the analysis of intensive longitudinal data, long longitudinal data. And then finally, this paper, which is coming out in Psychological Methods, I do believe. It will get through the review. And the paper that's the impetus for this web talk. So that's the paper that made me think about all of these different related topics for this web talk. So the paper is based on an idea that came to mind during a morning walk that I took in January 2019.